In this video, I will provide a quick introduction to the Cathode Ray Oscilloscope, or CRO. Then we will interpret and solve AICE Physics questions related to CRO screens and learn how to read the period and amplitude from the display. What is an oscilloscope? The word oscilloscope comes from two Latin roots, oscillo and scope. Oscillo means oscillate, and scope, observe. Oscilloscope means a device used to observe oscillations. What is it called? A CRO. CRO stands for Cathode Ray Oscilloscope. The C comes from cathode and the R stands for ray. The name originates from the cathode ray tube, or CRT, a glass tube used to display images in early oscilloscopes. The same technology was instrumental in J.J. Thomson's experiment, which led to the discovery of the electron. This breakthrough paved the way for the development of early televisions, oscilloscopes, and other measurement display devices. Today, tube TVs have been replaced by flat digital screens. And the CRO oscilloscope has also become slim and digital. An oscilloscope is an instrument used to visualize electrical signals as waveforms, which helps us understand waves' properties like period, frequency, amplitude, and wavelength. To project a waveform on the screen, the oscilloscope must be connected to a signal source, such as a sound wave, an electrical circuit, or an electromagnetic frequency signal. In this video, we will focus on learning how to read the amplitude and period of waves by interpreting the screen divisions, even though we won't be using a CRO in our physics lab. This will help you understand how to analyze waves' properties and apply them to AICE physics questions. Now that we have covered a brief introduction to the Cathode Ray Oscilloscope, or CRO, let's put our knowledge into practice. In the following slides, I will solve 23 multiple choice questions from past AICE Physics examinations. I will break down each question step by step, showing you how to extract key information and apply a method that works for any CRO-related question. Here is how you can maximize your learning. Pause the video before I reveal the answer. Try solving the question on your own. Compare your approach with mine and refine your strategy. Let's get started. Let me read the question. A microphone connected to the Y plates of the cathode ray oscilloscope is placed in front of a loudspeaker. So here is a picture to illustrate this story. The trace of the screen of the CRO is shown. So this is what we see on the CRO display. The time-based setting is 0.5 milliseconds per centimeters, which means horizontally, each square is equivalent to this value. And the Y plate, so which means each square on the vertical direction, is equivalent to 0.2 millivolts per centimeters. What is the frequency of the sound from the loudspeaker, and what is the amplitude of the trace on the CRO? So what this information has provided? Number one, the screen with a waveform and the value of each box in centimeters in the horizontal direction and vertical direction. Also has provided the value that we need to convert the horizontal direction, because time always run on the x-axis or horizontal direction, and has provided the value for each centimeters on the vertical direction, which is 0.2 millivolts per centimeters. And we also need to pay attention on the options that we have for answer. So it's asking two things, the frequency and the amplitude of this waveform on the screen. So that's what we need to do. First, we need to calculate the frequency, and we need to calculate the amplitude of this wave. To calculate the frequency, we first need to determine the period. To find the period, we need to identify one complete cycle or wavelength from the grid. Here is one. Always look at the graph and locate the clear cycle from the start to the end. In this case, we will count the number of boxes from trough to trough. Here, the cycle spans 6 boxes, and each box is labeled 1 centimeters. So one cycle is equal to 6 centimeters. The period is the time corresponding to one full cycle. Now we know the period is 6 centimeters. Wait a minute, but it's not period in seconds? You are correct. So we need to convert 6 centimeters in seconds using the time-based setting provided, which is 0.5 milliseconds per centimeters. So to convert these to seconds, we can multiply the correspondent of one cycle, which is 6 centimeters, times the time-based settings, which is 0.5 milliseconds per centimeters. So we are going to cancel centimeter with centimeter, and the result is 6 times 0.5 milliseconds. So I'm going to replace the prefix milli with its multiplier, which is times 10 to the minus 3. So the period is equal to 0.003 seconds. To calculate the frequency is very simple. We know the frequency is the inverse of the period. So the period from our prior calculation is 0.003 seconds. So the frequency is 333.3 Hertz. To calculate the amplitude, start by drawing a horizontal line at the center of the wave. Next, count the number of boxes from the crest to the horizontal line. In this case, the distance from the crest to the center line corresponds to 3 boxes. Each box is labeled 1 centimeter, so the amplitude is 3 centimeters. The Y plate setting provided is 0.2 millivolts per centimeters. To convert these to volts, we multiply 3 centimeters, which is the value on the grid of the amplitude, times the value for each centimeters converted to millivolts. So 0.2 millivolts per centimeters. We cancel centimeters with centimeters. So then we have 3 times 0.2 millivolts, which gives us 0.6 millivolts. So here is the result of our calculations. The frequency was 333.3 Hertz. So I see A and B is a very similar number, and the amplitude is 0.6 millivolts. So the correct option is A. Let's work on a similar question, but this time the display grid does not show centimeter marks on the horizontal and vertical axis. Instead, the question refers to divisions. Here is how we can solve it. So first, let me read the question. The diagram shows the waveform of a signal displayed on a cathode ray oscilloscope. The time base is set at 5 milliseconds per division. The Y gain is set at 5 millivolts per division. What are the amplitude and the frequency of the signal? So first, let's identify one cycle. You can pick any. I select this one. Now, to calculate the amplitude, we need to count how many boxes you have from this equilibrium line, or the line that divides the wave into two equal parts, to the crest or to the trough. So in both ways, we have 2 boxes. So in this case, we are going to call division. So 2 divisions times the Y gain. So the Y gain is, or how many, the equivalent for any division is 5 millivolts. So then we cancel division with division. So the amplitude is 10 millivolts. If I look at this table here, I can see option A and option B, we have 10 millivolts. What is going to determine the correct answer is the value of the frequency. So let's proceed to calculate the frequency. So right here, first you have to find the period, because you already selected here a cycle, so we can count here 1, 2, 3, 4. We have 4 divisions corresponding to one cycle. So the value of the time base, which is the horizontal one, is 5 milliseconds per division. We are going to cancel divisions, and the result of the period is 20 milliseconds. The frequency is the inverse of the period, so the frequency is 50 Hertz, which is option A. Now it's your turn. Please pause the video, answer this question before I review my solution. Okay, so let me read the question. The diagram shows the representation of a wave on the screen of an oscilloscope. So this time we have the value for each box, which is 1 centimeter. The Y gain is set to 3.5 millivolts per centimeter. What is the amplitude of the wave? Very simple question. Number 1, identify the center of this wave, which is it's called the equilibrium line. Is the line that divides the wave in 2 equal parts. So when we measure from this line to the crest, so that determines the amplitude. And also it's true when you measure from this line to the trough. So here we have 2 boxes, either way. So each box corresponds to 1 centimeter. So we have 2 boxes or 2 centimeters for the amplitude. Now we need to convert this to this set right here, 3.5 millivolts per centimeter. So that's how we do. So 2 centimeters times 3.5 millivolts per centimeter. We cancel the centimeter, both. And 2 times 3.5 millivolts gives us 7 millivolts. or option C. Easy. Now I want that you pause this video and try to answer this question before I review my solution. Let me read this question. An electrical signal is displayed on a cathode ray oscilloscope or CRO. The time-base setting is 50 milliseconds per division and the Y setting is 2 volts per division. What is the amplitude of the signal? So this question is asking just for the amplitude. So to determine the amplitude, you need to look vertically. In order to look vertically, let's establish our equilibrium line, or the line that divides the wave into equal parts. So it's very clear the amplitude here corresponds to one box or one division. The amplitude can be measured from this line to the crest or from this line to the trough. In both ways, the amplitude will be equal to just one box or one division. So, to convert the division into volts, we are going to do 1 division times 2 volts per division, which is the setting for the Y direction. We are going to cancel division with division, and the amplitude is 2 volts, or option A. Okay, I have here a question without a number. A cathode ray oscilloscope, CRO, is used to display the trace from a sound wave. The time base is set at 7 microseconds per millimeter. What is the frequency of the sound wave? I noticed that for the horizontal grid, the marker here is 2 centimeters and the vertical is 1 centimeter. But when we calculate the frequency, you have to look just the horizontal because we have to find first the period, correct? So, following the sequence of our strategy here, we are going to identify one wavelength. I think this is a good one. And we can clearly identify the beginning and the end. And we are going to calculate the period of this wave. So we have 1, 2, 3 boxes, right? Each box is 2 centimeters. So this corresponds to cycle, right? Will be 6 centimeters times the time base, which is 7 times 10 to the minus 6, because micro is a prefix, and here is replaced by its multiplier, which is times 10 to the minus 6 millimeter. Now we have 2 different units for length, so let's try to convert to the same unit. I will say it will be easier. 6 centimeters to millimeter, which is 60 millimeter. So now we can cancel millimeter with millimeter, and the result is 4.2 times 10 to the minus 4 seconds. Very good, but the question is asking the frequency. So we know the frequency is the inverse of the period. So the inverse of 4.2 times 10 to the minus 4 gives us 2.4 times 10 to the positive 3. So then that one will be kilo, right? So the answer for this question is 2.4 is C. Next question. The output of a signal generator is connected to a cathode ray oscilloscope, CRO. A trace is shown on the screen. The time-based setting of the CRO is set at 2 milliseconds per centimeter. What is the frequency of the signal? Now is the time of repetitive work. First, identify one cycle. This one is good enough. And now determine how many boxes I have in this cycle. So in this case, 1, 2, 3, 4. and each box is 1 centimeter, so the period is 4 centimeters times the time base setting, which is 2 milliseconds per centimeter. Cancel both centimeters, and the result is 8 milliseconds. To find the frequency is the inverse of period, and the inverse of 8 milliseconds, which is 125 hertz. Easy. Another is one. A cathode ray oscilloscope CRO is used to display the trace from a sound wave. The time base is set at 5 microseconds per millimeter. What is the frequency of the sound wave? Again, first find a cycle. Right here, good enough. And then count how many boxes I have in this cycle. 1, 2, 3. So each box is 3 centimeters. So the period is 3 centimeters. To convert to seconds, I have to use the time base settings, which is 5 microseconds per centimeters. Cancel the centimeters, so the period is 15 microseconds. 3 times 5 is 15. To find the frequencies, the inverse of a period and the inverse of 15 microseconds. Remember to replace the prefix micro to its multiplier when you type on your calculator, which is times 10 to the minus 6, and the frequency is this horrible number here, which is, let's see, 1, 2, 3, let me count one more time, 1, 2, 3, so looks like 67 kilohertz. So let me go for with option D. Another easy question for you. A microphone is connected to a cathode ray oscilloscope when a tuning fork is struck and then held next to the microphone. The following waveform is shown on the display of the CRO. The time-based setting is 2 milliseconds per division. What is the best estimate of the frequency of the sound produced by the tuning fork? So, same sequence. Identify any cycle of this grid, of this wave. So this is good enough. The whole idea is to know how many boxes corresponds to one cycle. In this case, 2 boxes, right? But I don't have the centimeters here, I have division. So these 2 boxes or 2 divisions, we need to convert to seconds to find the period. So right here, 2 divisions times 2 milliseconds per division. We cancel both division, and the period is 2 times 2, 4 milliseconds. But I'm looking for the frequency. So the frequency is the inverse of the period. So inverse of 4 milliseconds. Now, be careful. You need to replace the milli, which is a prefix, which is multiplier, which is times 10 to the minus 3. Take this in consideration when you type on your calculator. So the frequency is 250 hertz, which is option C. One more practice for you. I know you are getting tired of this because it's kind of repetitional. So a sound wave is displayed on the screen of a cathode ray oscilloscope as shown here. The time-based setting is 0.5 milliseconds per division. What is the frequency of the sound wave? What do we need to find first? You are right. Any cycle, any one, just to determine how many boxes I have in one cycle. In this case, we have 1, 2, 3. So 3 divisions, because now boxes is being replaced with the word division. So 3 division corresponds to one cycle or one period. To convert to seconds, we need to do this. 3 divisions times 0.50 milliseconds per division, and the period is 1.5 milliseconds. To find the frequency is the inverse of a period. Type in your calculator and you get 666.6 hertz, which is 670 hertz. Please try this by yourself before I review my answer. The diagram shows the screen of a cathode ray oscilloscope displaying a wave. The time base of the CRO is set at 10 milliseconds per division. What is the frequency? Number one, find one cycle right here. Now, this question is interesting because I have tried different ways and I cannot get the beginning and the end that hits exactly the box, the end of the box. So I can see it's a little bit over. It's okay. For this case, I'm going to estimate like 4 divisions. 1, 2, 3, 4. I know it's a little bit more, but that's okay. 4 divisions. Now I'm going to convert these to period. So the 4 divisions times 10 milliseconds per division, and this is 40 milliseconds. So cancel here, 4 times 10, 40. To find the frequency is the inverse of the period. So inverse of this is 25 hertz. Well, because I approximate, I need to find the value that is close to that, and I will say that 24 hertz is good enough for me. All right, now we have a square wave. So, how will you answer this question? So let's go. A cathode ray oscilloscope displays a square wave, as shown here. A time-based setting is 0.20 milliseconds per division. And what is the frequency of the square wave? All right, so let's follow the same sequence C as the prior questions. So is identify one cycle. Let's go. So here, good enough. Then we are going to calculate the period. So to find the period, you need to find how many boxes here correspond to this cycle. 1, 2, 3, 4, 5, 6. All right, so it's a division. Let's go. 6 division times the time-based setting, which is 0.2 times 10 is a multiplier here, right? So milli 10 to the minus 3, and we get period is 1.2 times 10 to the minus 3 seconds. Listen, if you want to use milli here, it's completely fine. So now to calculate the frequency, we are going to do the inverse of a period, which is 830 hertz, which is option B. How are you doing so far? We have spent 28 minutes learning this, so I'm sure that by now you know how to answer this question. So please pause the video, answer the question, and compare with my solution. So I'm going to read this question for you. A sound wave is detected by a microphone. The output of the microphone is connected to the Y input of the cathode ray oscilloscope. The trace of the CRO is shown. The time base is set at 0.2 milliseconds per division. And what is the frequency of the sound wave? Same step. Number one, identify one cycle because we need to count how many boxes correspond to one cycle. In this case, 4 boxes or 4 division. Now, we need to multiply by the time-based setting, which is 0.2 milliseconds per division. Cancel division, and the period is 0.8 milliseconds. To find the frequency is the inverse of the period. So the frequency is 1 over 0.8 milli. The multiplier is times 10 to the minus 3. take in consideration when you type on your calculator. So the frequency is 1250 Hertz. Please pause this video, try this question before I review my answers. Let me read this question. 4 cathode ray oscilloscope screens each display a waveform. 1, 2, 3, 4. The screen and the time-based setting of each CRO is shown. Which screen show waveforms of the same frequency? To answer this question, I have to calculate the frequency of each display and then compare to determine which displays have the same frequency. Screen number 1. I'm going to identify a cycle, and here we have 1, 2, 3, 4 divisions. So 4 divisions times the time-based settings, which is 0.02 seconds per division, is 0.08 seconds. And the inverse of this is 12.5 Hertz. For screen number 2, this is the cycle, which has 2 divisions. So 2 divisions times 0.04 seconds. So gives us a period of 0.08 seconds, which frequency is 12.5 Hertz. Screen number 3, this is one cycle, and we have here 2 divisions. So 2 divisions times the time-based setting, which is 0.01 second per division, gives us a period of 0.02 seconds and a frequency of 50 Hertz. And the last one, the screen number 4, this is the wave. We have 1, 2, 3, 4 divisions times 0.08 seconds per division, gives us a period of 0.32 seconds and a frequency of 3.125 Hertz. So to answer this question, the screens that show the waveform with the same frequency is screen 1 and 2, which is option A. Okay, so this question is a little bit different, so I'm going to read for you. A cathode ray oscilloscope, CRO, is connected to an alternating voltage. The following trace is produced on the screen. The oscilloscope time-based setting is 0.5 milliseconds per centimeter, and the Y plate sensitivity is 2 volts per centimeter. Don't worry about this word sensitivity. It's just one added word for no need. The question is, which statement about the alternating voltage is correct? So here is asking A. Let's take a look on A. The amplitude is 3.5 centimeters. So let's see if this is correct. So this is our line that divides the wave into 2 equal parts. And now we are going to measure from this line to the peak or to the crest, right? So here, let's count how many boxes we have here. 1, 2, 3.5. So the amplitude appears to be 3.5 centimeters. But wait a minute. We are giving a Y plate setting, which is 2 volts per centimeter. So that's not the value of the amplitude. Need to be displayed in volts. So how we do that? So we are going to calculate the amplitude based on the setting that was given in the question. So 3.5 centimeters times 2 volts per centimeters gives us 7 volts. So this option A is incorrect. Now let's take a look on option B, right? To determine option B, to find the frequency, you need to find the period first. So to find the period, we need to identify one cycle. So let's make this here a cycle to determine how many boxes or divisions are in this cycle. So 1, 2, 3, 4, right? So 4 centimeters correspond to one cycle, and we want to find the period. So doesn't make sense that a period is 4 centimeters. We need to convert to seconds, just like we did with amplitude. So the time-based setting is 0.5 milliseconds per centimeter. So let's do this. So the period is 4 centimeters times the time-based setting, which is 0.5 milliseconds per centimeter. So the period is 2 milliseconds. Great. To find the frequency, which is the inverse of a period, is 1 over 2 times 10 to the minus 3, because milli is 10 to the minus 3, which gives us a frequency of 500 hertz. But here is 0.5 kilohertz. It will be the same? Yes, it's the same. So 0.5 kilohertz is the same as 500 hertz. So this statement is correct. Now, the C is say the period is 1 millisecond. Definitely is not. So we found the period is 1 millisecond and the wavelength is 4 centimeters. Technically, we cannot calculate the wavelength because the wavelength is measured horizontally, and horizontally here is we are having time, not length. So the correct answer is B. All right, back to the easy question again. So try this question before see my solution. Pause the video and then replay the video so you can see how I answer this question. Let me read this question. A signal of frequency 25 Hz is displayed on the screen of a cathode ray oscilloscope. What is the time-based setting? Okay, so in order to find that, we need to identify a cycle. This one is good enough. So now we have 2 boxes. Each box is 1 centimeter. So we have one cycle corresponds to 2 centimeters. But the frequency was provided. So what we can do with that? So the frequency is 25 Hertz, which means the period is the inverse of a frequency, which is 0.04 seconds, right? So to find the time-based setting, we need to divide 0.04 seconds by 2 centimeters. So we have 0.02 seconds per centimeters, which is the same as option B. So let's see how you do now. The same question that we did before, here we need to find the time-based setting again. So pause the video and try yourself. Now I'm going to read this question. A sound wave of frequency 270 Hz, you see the frequency is provided, is recorded by a cathode ray oscilloscope CRO. The waveform on the CRO is shown. What is the time-based setting on the CRO? We need to identify one cycle. So right here is 1. But it's not exactly what I was expecting, because here is 1, 2, 3, 3.5, a little bit more. 1, 2, yeah. So let's see how we get from this. So number 1, we know that the frequency was provided, and then we can find the period from there, right? So the frequency is 270, so the period is 0.0037. To find the time-based setting, I'm going to divide the period, which corresponds to this wave, by the number of boxes here, which appears to me 3.6. Okay, let's try that one. So if I divide the period in seconds by how many boxes I have here for one cycle, which is 3.6 centimeters. So I have 0.001 second per centimeter, which we can mark option B, which is the same thing. Okay, now is a repetition again. So pause the video, try yourself, come back to me. Let's see how we do it. I'm going to read the question. A cathode ray oscilloscope CRO is used to display a wave of frequency 5 kilohertz. The display is shown here. What is the time-based setting of the CRO? So it's asking pretty much on the horizontal direction, not the vertical one, right? So we are going to first identify one cycle which corresponds to 2 boxes or 2 centimeters. The frequency was provided 5 kilohertz. So the period is 0.0002. I'm sure you know how to calculate at this point. The period is the inverse of the frequency. To find the time-based setting, we are going to divide this period by the corresponding number of boxes, which is 2 or 2 centimeters. So when we divide, the answer is 0.0001 seconds per centimeters, which correspond to option B. Look at this story. A cute whale produces sound waves of frequency 5 Hz. The waves are detected by a microphone, and in this case connected to the CRO, and displayed on an oscilloscope. What is the time-based setting on the oscilloscope? All right, identify a wave. So I have 2 boxes or 2 divisions because this time I don't have centimeters. So 2 divisions, and I have the frequency. So the frequency is 5 Hz and the period is 0.2 because period is the inverse of 5 Hz. And to find the time-based setting is 0.2 seconds, which is the period divided by the number of divisions corresponding to one cycle, which is 2. So that is 0.1 seconds per division, which is the same as option D. One more for you to practice. I'm going to read this question. A cathode ray oscilloscope CRO is used to display a sound wave of frequency 2000 Hz. The display of the CRO is shown. What is the time-based setting on the CRO? Find a cycle. 1, 2, 3, 4 centimeters correspond to this cycle. But the frequency was provided, so we can find the period. So to find the time-based setting, we divide the period by the corresponding number of boxes for one cycle, which is 4 centimeters. So then we have 0.0000125 seconds per division, which is the same as option A. This question is a little bit different. So if you want to look, can try, but let's see how we solve this. I'm going to read the question. A student uses a cathode ray oscilloscope to measure the period of a signal. She sets the time base of the CRO to 5 milliseconds per centimeter and observes the trace illustrated below. The trace has a length of 10 centimeters. What is the period of the signal? All right, so I need to identify the value of one cycle here, but at this time, this is giving centimeters, right? So let's see what we can do. So here is, I can visualize better if I draw this equilibrium line. So now I can identify the number of wavelengths. So let me count. 1, count with me actually. 1, 2, 3.5. All right, so 10 centimeters divided by 3.5 So one wavelength has 2.857 centimeters. All right. So now the period corresponds to one wavelength or cycle. The period is 2.857 centimeters times the time base, because now I want to convert the centimeter into seconds, which is a unit for period. So I cancel centimeters with centimeters, and the period is 14.28 milliseconds. Or the period is 14.28 times 10 to the minus 3 seconds. Or option D. All right, so this question is a little bit different. Stick around and I'm going to explain to you how to solve it. Let me read the question. A cathode ray oscilloscope, CRO, displays a waveform as shown. Here we have two pulses or peaks. The time interval between two adjacent peaks of the waveform is 0.006 seconds. What is the time base setting of the CRO? So here is the distance between both peaks. In terms of boxes or divisions, we have 1, 2 for sure, and we have half here and half here. So we have 3 boxes or 3 divisions between both peaks. And the time interval between two adjacent peaks, in this case, is 0.006 seconds. So to find the time setting, we are going to divide this time by the number of the divisions. So it is 0.002 seconds per division, which corresponds to 2 milliseconds per division. This one is simple, but I need to explain to you. The diagram shows two complete pulses, see complete, on the screen of a cathode ray oscilloscope. A grid of 1 centimeter squares covers the screen. The time base setting is 1 microseconds per centimeters. How long does each pulse last? Okay, this is a pulse, so this is how long it lasts. Is 2 boxes or 2 centimeters, right? So in this case, lasts 2 centimeters, but is asked in terms of time, not in terms of centimeters. So how we do that? We need to convert. So to convert 2 centimeters in microseconds, because all the answers are in microseconds, we are going to multiply the 2 centimeters times the time base setting, which is 1 microsecond per centimeter. We are going to cancel centimeters, and a pulse lasts 2 microseconds on option A. Pretty easy, but you need to be explained. Someone needs to explain to you how to do it. We have finally reached the end of this video with this question. So let me explain to you. A transmitter emits a pulse of electromagnetic wave towards a reflector. So I'm here following this diagram that I did for you. The pulse is reflected and returned to the transmitter. And there is a detector located at the transmitter. The emitted pulse and the reflected pulse are displayed on the cathode ray oscilloscope as shown. The pulse takes 6.3 microseconds to travel from the transmitter to the reflector. From here to here takes 6.3 microseconds. What is the time base setting of the CRO? Okay, so let's say this is pulse 1, which is the transmitted pulse, okay? Transmitted from the transmitter to the reflector. And this pulse 2, let's say this is the reflected pulse, the one that comes back to the detector. And the time interval between the transmitted and reflected is 6.3 microseconds. Okay, so to find the time setting, you are going to divide 6.3 microseconds by the distance between both peaks. So we have here 1, 2, 3 centimeters. So this division gives us 2.1 microsecond per centimeter, or option A.